Hi everyone. This tutorial is about acids and bases, and we'll also be looking at the pH scale. Now your reference for acids and bases is chapter 7 in your textbook. We won't be covering everything in that chapter. We're just going to hit on a few of the key topics that you would need to know to carry on with your chemistry studies. So let's begin by looking at acids. Acids contain the hydrogen ion, or the H plus ion. And that hydrogen ion will be bonded to an anion, a negative ion. And that anion could be an element, like in the case of let's say a chloride ion or a fluoride ion or the sulfide ion, or the hydrogen ion could be bonded to a polyatomic ion. So here are some examples down here. This first one, hydrochloric acid, it has the formula of HCl. So it's just the hydrogen ion, and then you crisscross that with the chloride ion to give you the HCl formula. Sulfuric acid, it doesn't begin with hydro, so that tells me that it's an acid with a polyatomic ion. And because it's an ic acid, I know that it's with the sulfate ion. Now, we used to, in the old curriculum, have grade 10 students learn this nomenclature for acids. It's no longer in your curriculum, so I don't make it a prerequisite for testing. I'm not going to ask you to write chemical formulas for acids. If you were writing an equation that involves an acid, I would give you the chemical formula for the acid. The next one is nitrous acid. So nitrous, because it ends in OUS, I know that it is with the nitrite ion, and so its formula would be HNO2. And remember, we've talked about this in class. These acid formulas will have AQ written after them. It's not a big deal that you guys are doing that, but just if you see these in writing, you'll know what it means. And acids are always in an aqueous form, meaning they are the acid compound dissolved in water. Citric acid, I forgot to look this up before I did the video, but I don't know its formula. But citric acid is the acid you find in citrus fruit, and it's also the acid that gives sour candies their sour flavor. And the last one is acetic acid. And I believe it's C2H3O2. Sorry, that's a bit messy. C2H3O2. So it's the acetate ion with the hydrogen ion. So it looks something like, oh, I might be messing this up, something like that. Okay? And so you crisscross those ions together and you get acetic acid. And acetic acid is just the chemical name for vinegar. So these are some common acids. What you will notice in their formulas is that they have the hydrogen ion in them. Now our bases usually contain the hydroxide ion. So here's our OH hydroxide ion, but there are other types of bases that are not hydroxides. They may contain polyatomic anions like carbonate, and I can't do subscripts in this program, so I'm just going to write them in. Oops, sorry, not CO2. So it's CO3 2 minus is the carbonate ion, or bicarbonate. So bicarbonate is HCO3 1 minus ion. And these are all on your yellow sheet of polyatomic ions. But these are the anions that form bases. Now the cation part of the base could be any metal. Okay, so here are some examples here. We've got sodium hydroxide, which is NaOH, so that's the sodium ion with the hydroxide ion. NaOH. Sodium bicarbonate is NaHCO3, so it's with the bicarbonate ion. That's baking soda. And calcium carbonate is CaCO3. Both calcium and carbonate both have a charge 2, so we end up with CaCO3. Calcium carbonate is limestone, so it's a big part of what is in our drinking water. It's what forms that scale in your kettle when you get that white crusty stuff in your coffee maker, your kettle, or your irons. That's calcium carbonate. It's dissolved in our drinking water because our water comes from groundwater or the lake, and our bedrock is limestone. There's a lot of calcium carbonate dissolved in our water, and we see that coming out in our appliances sometimes as that white scale. So these are some common bases, with showing you both the hydroxide type of base as well as the bicarbonate and carbonate bases. Now, acids and bases differ in their properties. They're both types of ionic compounds, but their properties are quite different, both their chemical and their physical properties. So I've just created this T-chart here just to compare their properties. So acids, they taste sour, like that citric acid or vinegar. It's got that sour taste. They are corrosive, so they will corrode skin, they will corrode surfaces like even metal. They react with metal quite well. Their pH will be less than 7, somewhere between 0 and 7, and the closer the number is to 0, the stronger the acid. Acids are good conductors of electricity because they are ionic compounds, and ionic compounds are good conductors. And acids will, and this is new to you guys, acids will turn blue litmus red. So litmus is an indicator. It's a chemical indicator, and there's two kinds of litmus. There's blue litmus and there's red litmus. We use blue litmus to see if something is an acid. If it turns to red, then we know that solution is an acid. Over on the bases column, bases tend to taste bitter. To give you an example, soap is made from a base. It's usually potassium hydroxide that's used to make bases slippery, and therefore they lather up really nicely. But if you've ever tasted soap, it tastes bitter. Bases are also corrosive. A lot of people don't realize this. They think that just the acids are corrosive, but bases are equally corrosive when it's a strong base. For example, bleach is a strong base, and you would never put your hand in bleach and leave it there. You would end up with a pretty nasty chemical burn. Bases have a pH greater than 7, so their number will be somewhere between 7 and 14. They are also good conductors of electricity, and that's because they are ionic compounds. Like I mentioned, they feel slippery to the touch. And then down here we've got this litmus comment. So red litmus is the other type of litmus. It's a chemical indicator. When red litmus turns blue, you know that your solution is a base. And the way that I remember these two relationships about litmus is that red turning blue, blue starts with a B and so does bases. So that's the connection for me to help me remember that. Blue litmus turns red, red ends in D, and so does acid. So just some quick little mnemonic device to help you remember what happens with litmus. So now we've talked about acids and bases, we're going to look at the pH scale, and this is our scale of measurement that we use in chemistry to indicate the relative strength or weakness of different acids and bases. So this expression here, pH, notice it's a small p and a capital H, so please always try and write it that way. I learned it as it stood for the power of hydrogen, but as I've read a little bit more, that P actually doesn't represent power. It comes from a Danish word for strength, so it literally translates to the strength of the hydrogen ion. So the more hydrogen ions that there are in a solution, the more acidic it is. Interestingly though, the more hydrogen ions there are, the lower the pH number. So a solution with a pH of 0 or 1 or 2 is a very strong acid, and that would mean that it's actually very high in hydrogen ions, or the concentration of hydrogen ions is very high. Another interesting fact about the pH scale is that it's a logarithmic scale. So see this word here, logarithmic? It is not a linear scale. So when we look at the pH scale, it runs from 0 to 14, with 7 being in the middle. So each step of 1 on the pH scale does not represent a difference of 1 times. For example, 3 is not double the pH of 1.5, but it's actually a 10-fold difference in acidity or basicity on the pH scale for every step on the scale. So if we are comparing a pH of 4 to a pH of 5, a pH of 4 is 10 times more acidic than a pH of 5. If we move 2 places along the pH scale, a lot of students will conclude that it's 20 times more acidic, but that's not correct. We have to multiply 10. It's an exponential difference. So if I go from a pH of 5 and increase the acidity down to a pH of 3, because remember the closer we get to 0, the stronger the acid. So if I move down to 3, I've moved 2 steps along the pH scale. That would mean that that pH of 3 is 100 times more acidic than a pH of 5. We see the same relationship as we move the other way on the scale up to 14. Now this is the basic end of the scale, or the alkaline end of the scale, but each step represents an increase in basicity or alkalinity of 10 times. So here's a diagram of the pH scale, and you can see that it's going from 0 to 14. Neutral is right in the middle here at 7. So not many things in our world are at 7, right at neutral, but pure water is neutral. That's just about the only thing out there that's neutral. So we're not talking about tap water here, and we're not talking about rainwater, pond water, lake water, because those forms of water all have different ions dissolved in them that change the pH. But the bottled water you might buy that's distilled water, now not your general bottled water, that's actually just groundwater that they're putting into bottles. You might as well drink from the tap, it's the same thing. But if you buy distilled water, it has a neutral pH of 7. Everything below 7 down to 0 is acidic, and the closer you go to the end of the scale towards 0, the stronger the acid. Anything that's close to 7 is a weak acid. On the other side, you can see they have the word alkaline here. Well, that's the same thing as base or basic. Okay, those words mean the same thing. And as we go towards the end of the scale, we get into these really strong bases. So you can see some common materials. At the very end of the acidic scale right down here, here's pure hydrochloric acid. Very concentrated, strong hydrochloric acid. Now this is the acid we have in our stomach. It's not at that high of a concentration, but it is a pretty strong acid. Up at the extreme end, up at the basic end at 14, I can't really read what's on the label here, but I imagine it's probably concentrated sodium hydroxide. But you can see oven cleaner and bleach and ammonia. Those are pretty strong cleaning products. Because they're at the top end of that pH scale, they're strong bases. But baking soda is pretty mild. Eggs, we eat eggs. We use egg whites in cooking. It's not that strong a base. Down in the acid end, a lot of our fruits and vegetables are acidic. It's actually healthier to eat a more alkaline diet in terms of overall health and in fighting cancer in particular. But some of these acidic products are down here, like tomatoes, and lemons, of course, are very acidic because of citric acid. So this gives you an idea of how the pH scale is arranged and what some of our common products are in terms of their pH. So this slide is just a quick review about what the numbers on the pH scale mean. So I have two questions here for you to think about. The first one is, how many more times acidic is lemon juice, which has a pH of 2, compared to tomatoes, which have a pH of 4? So this is a difference of 2 on the pH scale. Remember I said each step on the pH scale is a difference of 10 times? So lemon juice is actually 100 times more acidic than tomatoes. 100 times more acidic. It has 100 times the concentration of hydrogen ions compared to tomatoes. The second question, how many more times less basic is pure water compared to ammonia? Ammonia has a pH of 11. Well, what was the pH of water? Pure water. It was 7. It's neutral. So we're comparing 7 to 11. And that's a difference of 4 steps along the pH scale. So what we need to do is take the number 10 to the power of 4. And so what this gives you is 10,000 times. A quick way that you can figure out how many times, if it's a big number, is just the power, like we had 4 in this case, represents the number of zeros in your answer. So it's a 1 and that many zeros. So we have 10,000 times. So pure water is 10,000 times less basic than ammonia. And so that gives you an idea of just how strong ammonia is. Now this last slide is a little bit of a bonus. I'm just going to show you how we calculate pH. And we don't do this calculation formally until grade 11 chemistry, but I do like to introduce it to grade 10s. This concept of logarithmic scales is fairly new to you guys. I don't think you've studied it in math yet. You will study it in more advanced math classes. But this is the calculation right here for finding the pH of a solution. What you do need to know is the hydrogen ion concentration, and that's what's here. This square brackets with the H plus symbol represents the hydrogen ion concentration. And the way we calculate pH is it is equal to the negative log of the hydrogen ion concentration. The log symbol is on your calculator. If you have a scientific calculator, you'll find it on there. And depending on your calculator, you either put in the concentration first or and then press the log button, or you have to press the log button first and then put the concentration in. It just depends on your calculator. You'd have to play around with it. And I can't do superscripts or subscripts on this app, so I've just, if you notice right here, I've used that little hat symbol, which means exponent. Okay, so the question is, what is the pH of a solution containing 1.00 times 10 to the negative 3? And I didn't put units in here because it's not something you guys would know or understand. We teach this in grade 11, but the unit is called moles per liter. It's a unit of concentration that we deal with solutions. So here's our solution down at the bottom to this solution problem. pH is equal to the negative log of the hydrogen ion concentration. All I did was sub in the hydrogen ion concentration here. And when you take the log of 1.0 times 10 to the negative 3, you get an answer of negative 3. But remember, there's this little negative sign at the front of the formula. So what we're doing is applying a negative to a negative, which gives us positive 3. You'll notice there's no negative numbers on the pH scale. Okay, there's only positive numbers, and that's why we apply a negative sign to it. So if we have a solution with a concentration of hydrogen ions of 1 times 10 to the negative 3 moles per liter, that would have a pH of 3. Okay, so it's just a bonus thing. Those of you that are real math nerds like me, you might have been curious to know, how do they find pH? It's just these random numbers. Well, it's not random numbers. It's a logarithmic calculation based on hydrogen ion concentrations for that solution. The bigger this number, the bigger the hydrogen ion concentration, the lower the pH value, and it's because we're taking a logarithm of this. Okay, so that's it for acids and bases. We'll be doing some questions based on this in class tomorrow.